Thank you. I have to start by apologizing. My colleague Josh cannot be here for his part of the presentation today. He's the Raman expert, but I guess we'll have chances to speak to him. And if you have any difficult questions, I will try to give you the answer back, even if it has to be, a little bit later. But today I wanted to talk to you a little bit about the correlative workflow using Raman and backscattered electron and X-ray imaging for analyzing the composition of the bone implant interface. So just a quick summary. I'm just going to give a quick introduction to BEX, what is BEX and what is Raman imaging, because I guess most people are more electron microscope based, and then a little bit of some applications with RISE. Then I'll go into this bone implant project and try to convey the challenges of this type of multimodal workflow, but also the good outcomes that we can get. So let me start this video here. So this video is just to show you what BEX is, and it's a combination of backscattered electron and X-ray signals. The idea here is that you collect your characteristic X-rays for the composition, and you acquire simultaneously your backscattered image. So there's no limitation here because you are working at the usual speed that you will be doing your backscattered imaging. So you have your BEX image, which is a colored image by element with atomic contrast and also with topographical contrast. And the advantage here is that we can go really, really fast. So for scanning large samples, like the example that I'm going to give later on, it's going to be key to use this sort of technique. And if you see here, usually you can get a very nice full map of all your samples in the time that it takes to go and have a coffee. I want to start by showing you a cool example using BEX. This is collected by Louise and Rob Kessler here in our demo center, which is a birch seed collected actually, I think, from Rob's car. And Louise and Rob were looking at the contamination particles in this. And here it was taking advantage of BEX to image a millimeter size sample that it has a complex topography, but because of the geometry of our BEX detector, we don't have so much shadowing, or we don't have almost any shadowing collecting the BEX signal, and you can quickly target in higher resolution regions of interest that you can identify using the quick screening. All right, so that's a little bit on BEX. And just to give you another example, here you see an example of a bone with a titanium implant and magnesium implants. If you take a look again, this is a millimeter sized scale bar. And here, again, we do within 1 hour using our BEX detector, what we usually would do around 48 hours with the EDS alone. So mapping is really, really much faster. The advantage is also because sometimes with the biological samples, you struggle with a beam, with putting too much energy in. Because you go so fast, you actually end up putting less damage on your sample. And you can also work on low vacuum mode. So that can be really, really cool if you have that option in your microscope. So here, these implants have titanium, where you can see this large cyan implant, and then you can see the degradation of magnesium implants that are dispersed in the tissue. And the advantage here is that on the atomic contrast alone, we wouldn't be able to distinguish the magnesium implants being degraded. For RISE, so I want to talk to you a little bit about this multimodal solution called RISE. It's Raman Imaging and Scanning Electron, and this is just integration of a confocal microscope on the SEM chamber. So here, what you do is that you get the signal from your electron microscopy, and you combine it with the signal from your Raman. A little bit on the difference between EDS/BEX and Raman here. So as we know, with EDS, you can get the atomic composition, you get your characteristic X-rays, so you can find what is in your sample. With Raman, you are looking at different bonds. So you look at vibration modes and how the light from the laser is scattered when it interacts with the molecule. This gives you a Raman shift, and by the Raman shift, you can actually collect the molecular fingerprint of the molecules that you are imaging. But what's the advantage here? So you want to combine actually the best of both, because as it's been shown in the past many times, when you have integrated solutions, you might have to lose and you might have to compromise a little bit. And here we don't want to have any of that. So we want to have both the quality of the SEM and both the quality of the rice system. So what happens here is that the microscope stage will be able to shuttle from the SEM column to under the Raman lens. And you want, of course, to acquire all is the same point of interest. I'm not going to go too much on how we do this correlation, but this is attached to just a piezo scanner, and you'll be able to get a good range in the X, Y, and Z planes. So you have the traditional SEM advantages combined with the confocal Raman advantages here. So some cool examples. This is an example looking at structure of this aragonite platelets, and this is looking at the pearl. And what we could see with the Raman imaging was actually giving rise to this crystalline structure that you see here represented by hexagons. You actually have two different arrangements of the crystal, and this is what gives you this different structure. And you can, if you zoom in on the Raman spectrum, you can actually visualize the difference here, revealing on how these crystalline structures are generated. So another cool example is sometimes it's difficult to find differences just by ultrastructure alone. And here is an analysis of hamster brain tissue, where you are able to distinguish between gray brain matter and white brain matter by looking at the Raman spectrum. So you can know which type of cellular tissue you're looking at. And if you want to go higher resolution, you can go higher resolution. This is just an example of how E. coli strains were characterized and differentiated using one of these rice solutions. Something that I forgot to highlight as well is that these systems are kind of microscope agnostic, so you can go on different microscope strands, but we can talk about that later on if you'd like. For the bone implant project, then we wanted to look at this hydroxyapatite implants and see are they promoting bone growth and healing? What's going on around the implant? How does the bone and implant interface look like? So we thought, okay, we need a workflow that will allow us to look at this. So we decided to go for this Raman rise using our BEX multimodal imaging. And I want to give you here, I think this is kind of the main slide of the presentation, because I want to focus on the different steps of the multimodal workflow. So the first challenge, of course, with biological samples is always the sample prep, right? And here we have a big challenge because the samples are really, really large. We're talking centimeter scale bones, and we needed to prep them in a way where they were stable under the beam, but still we were able to image with Raman. This means that we cannot do any coating of the sample, or else we cannot have a good Raman scattering to identify our molecules of interest. So we have a polished sample embedded in resin, but without any coating. That is really large, so not really very conductive, and we need to find a way to image it. Because the sample was so large and difficult to handle, we decided that maybe the best approach is actually taking advantage of the speed of BEX and use that to have a map and see if we can target regions of interest. And this was really, really good because we needed to go fast, low energy. We don't want to also have any knock-in effects, because that's also gonna compromise what you can do on the Raman imaging. The sample again is uncoated, and we have to somehow find a way to pick regions of interest. But because we get the chemical imaging at the same time as our backscattered image, we start to be able to distinguish bone from these hydroxyapatite implants. After we did the mapping of the full sample surface, we were able to pinpoint 10 regions of interest. Then life gets a little bit easier when we want to get to the Raman, which Here I put the example. You can do either on a rice system or not. If you have a standalone rice system, you can just load the Bex maps and use that to navigate your sample. So when we were able to pick the region of interest with a bone and implant interface, we did the Raman imaging here. And after having the Raman imaging, then it's safe, let's say, to give a little bit more dose and go a little bit harsher on your sample. So we still image the sample with variable pressure mode, but we could go for longer imaging times, collect higher resolution, higher counts, so that we could go quantitative in our analytical workflow if you wanted to. After that, the only thing that's left, of course, is the correlation, which if you have enough images and enough features that you can recognize in every single modality, can be done more or less easily. And here we used our correlative solution Relate, and we find multiple points and we were able to match the data sets. So you are able to load the data from DDS. You are able to even load the picture that you see there before loading the sample that we use to navigate. So everything can be easily implemented so that you are able to actually get correlation of super large centimeter wide samples, but going to nanometer resolution electron images. So we're really going across scales here. So I just want to give you a little bit of a teaser of what we found using this workflow. We using our RBEX, we quickly mapped, we combined the EDS and BEX, and what we were able to see, and you can see this transition zone here in the middle panel and then enlarged on F and G, is that we found some molecules accumulating around the implant, and they have a spectrum that was characteristic of collagen, and it seems that we could find in the interface between bone and implant the features of actually promotion of bone growth. We looked also at a few different time points, and we tried to characterize this a little bit better. Unfortunately, that would be way too long for today. But if you want to know more about this story, we will be presenting a little bit longer story at M&M. And if you want to know a little bit more about Raman, you might be able to actually speak to George at M&M. And if you want to know a little bit more about multimodal applications on SEM, please say hi to me at M&M. I'll be happy to meet you. Thank you.